Search algorithms for pathfinding when navigating complex environments. From maze solving to GPS navigation, efficient search algorithms become indispensable tools. These algorithms determine optimal routes, avoid obstacles, and minimize traversal time. Their impact spans robotics, artificial intelligence, and geographic information systems. The distinction between uninformed and informed search lies in whether the algorithm leverages domain-specific knowledge. Uninformed methods rely solely on problem definitions, while informed approaches incorporate heuristic estimates to guide decisions. Understanding these categories provides insight into selecting the right tool for any task. Foundations of search algorithms. At their core, search algorithms solve problems by exploring states and transitions between them. Each state represents a configuration, and actions define possible moves from one state to another. The goal is to find a sequence of actions leading to a solution, a target state satisfying predefined criteria. This exploration occurs systematically, avoiding redundant paths and optimizing for speed or accuracy depending on constraints. Two primary paradigms emerge: exhaustive search methods that examine all possibilities and heuristic-driven approaches that prioritize promising paths first. State space representation. Problems are often modeled as graphs, where nodes represent states and edges symbolize permissible actions. This abstraction simplifies analysis but introduces scalability challenges as node counts grow exponentially. Traversal patterns dictate how efficiently solutions can be found. Depth-first search plunges into branches until dead ends, while breadth-first explores level-by-level expansion. Both have distinct advantages and drawbacks tied to memory usage and completeness guarantees. Breadth-first search, BFS, guarantees shortest path discovery in unweighted graphs but consumes significant memory, storing entire frontiers. Depth-first search, DFS, requires minimal memory but risks infinite loops and lacks optimality assurance. These fundamental algorithms form building blocks for advanced variants that address limitations through hybrid designs or additional parameters like cost functions and pruning mechanisms. Evaluating algorithm efficiency. Performance assessment requires considering time complexity, space consumption, and solution quality measures. Time complexity varies widely, from linear progression in best-case scenarios to exponential growth with increasing problem size. Space complexity becomes crucial in large-scale applications. Breadth-first search necessitates O(b) to the power of d, storage for branching factor b and depth d, whereas iterative deepening mitigates this issue by limiting recursion depths incrementally. Certain applications demand guaranteed optimal results regardless of computation overhead. In contrast, approximate solutions suffice for real-time systems prioritizing rapid responses over absolute precision. Time-space trade-offs. A classic example involves route-finding tasks. A car navigational system may tolerate slight detours for faster recalculations, whereas self-driving cars must guarantee safety-critical optimality. Balancing these priorities defines suitable algorithm selection. Informal benchmarks suggest BFS outperforms DFS in small-scale problems due to its systematic nature, although neither method scales well without modifications. Advanced algorithms frequently combine strengths of multiple paradigms to overcome individual weaknesses. Symmetry exploitation can dramatically reduce workload by identifying equivalent paths early in the process. This concept manifests clearly in graph traversal scenarios involving identical nodes configurations. Informed search strategies. Hill climbing exemplifies greedy algorithms that always select locally optimal steps toward global objectives. While efficient in many instances, this approach falters when local optima prevent reaching true minima or maxima. Simulated annealing introduces randomness into hill climbing, allowing occasional uphill movements inspired by metallurgy processes. This stochasticity enables escaping shallow local minima at controlled rates determined by temperature parameters. Heuristic functions. Guiding search directions effectively relies on estimating remaining distances to goals. Admissible heuristics never overestimate actual costs, ensuring correctness even amid approximations. Misleading heuristics may lead agents astray despite appearing reasonable initially. Validating estimates against known lower bounds proves vital for reliability in critical operations like autonomous vehicle routing. Euclidean distance, straight-line distance calculates idealistic minimum travel lengths applicable primarily in continuous spaces devoid of obstacles. Manhattan metric, sum of axis-aligned distances suits grid-based worlds commonly encountered in urban navigation contexts. Weighted asterisk algorithms assign modifiers to raw estimates, adjusting exploration intensity based on environmental factors affecting movement costs dynamically. Dijkstra's algorithm and its extensions René Descartes' influence extends indirectly via coordinate geometry foundations supporting modern pathfinding methods. Dijkstra's original paper addressed shortest path problems in networked systems with varying edge weights. The algorithm initializes distances arbitrarily, then iteratively selects nearest unvisited nodes, updating reachable neighbors accordingly. This priority queue management strategy ensures optimal solutions emergence in acyclic graphs. Complexity analysis, standard implementations exhibit O, V plus E, log V, time complexity assuming Fibonacci heap optimizations. For sparse graphs, this remains efficient compared to alternatives lacking comparable guarantees. Limited memory versions exist sacrificing perfect optimality for reduced runtime expenses. Such compromises prove acceptable when near-optimal outcomes outweigh exactness demands. Floyd-Warshall algorithm overview. Floyd-Warshall computes all pairs' shortest paths using dynamic programming principles. It builds upon successive intermediate vertices, improving existing estimates progressively. Despite cubic time complexity limitations, its simplicity makes it appealing for dense networks where multiple source-destination pairs need simultaneous resolution. The matrix multiplication analogy reveals deeper structural similarities with conventional arithmetic operations applied differently across adjacency matrices. Its robustness handles negative weight edges provided there exists no negative cycles. Detecting such anomalies forms integral parts of pre-processing phases before executing computations. Modern applications in robotics, autonomous vehicles employ hierarchical architectures combining high-level planners utilizing RRT*-based sampling methods alongside low-level controllers managing motor torques and sensor feedback. In warehouse automation, multi-agent coordination necessitates conflict-free trajectory generation among hundreds of robots working concurrently without collisions. Vision-based localization integrates feature-matching algorithms, augmenting traditional odometry measurements, reducing drift effects in long-term deployments. Sensors fusion improves environment perception capabilities, enhancing obstacle detection accuracies up to 98% according to recent industry reports from ROS Industrial Consortium members. Emerging research directions. Quantum computing promises dramatic improvements through superposition, enabling parallelism unachievable classically. Current research focuses on developing Grover-like oracle constructions tailored specifically for spatial reasoning tasks. Federated learning frameworks allow distributed training without centralized data aggregation. This privacy-preserving paradigm holds promise for collaborative mapping efforts respecting location confidentiality. Graph neural networks demonstrate capability extracting latent structures from connectivity patterns, potentially replacing traditional tree search methodologies soon. Ongoing work explores integrating classical AI techniques with reinforcement learning paradigms to develop adaptive agents capable of evolving behaviors in response to changing surroundings autonomously. Implementation best practices. Selecting appropriate data structures determines runtime characteristics significantly. Priority queues implemented via binary heaps yield sufficient performance for most practical implementations and less extreme scale requirements apply. Effective debugging requires careful visualization of explored regions, highlighting revisited locations, indicating inefficiencies warranting algorithm revisions. Tuning hyperparameters like epsilon values controlling exploration-exploitation balance plays crucial role in success probabilities, particularly in stochastic environments. Code modularity facilitates experimentation, comparing alternative approaches, easily swapping components responsible for evaluation function calculations or successor state generations cleanly. Evaluation metrics and testing frameworks measuring solution qualities demands consistent baselines. Common metrics include average path lengths, percentage completion rates, and CPU utilization statistics monitored over extended test durations. Unit tests verify basic functionality before proceeding to integration testing stages, verifying component interactions correctly align with theoretical expectations. Stress testing exposes vulnerabilities, revealing unexpected behavior arising from edge cases developers might overlook inadvertently. Benchmark suites compare relative performances across platforms, ensuring compatibility across diverse hardware configurations typically encountered in embedded systems domains. Common pitfalls and solutions: overlooking domain constraints leads to non-viable results requiring additional post-processing steps, correcting unrealistic assumptions made by simplistic models. Misconfigured heuristics produce erroneous guidance, causing divergence from intended targets, resulting in failed missions, wasting scarce computational resources unnecessarily. Incorrectly implemented loop prevention mechanisms mistakenly discard legitimate options, prematurely hampering overall solution finding abilities severely. Poor random seed selections introduce variability, undermining reproducibility concerns, impacting scientific validity of comparative studies conducted amongst competing approaches. Future trends in search technologies: advances in neuromorphic engineering mimic biological brain activity, offering energy-efficient pattern recognition capabilities exceeding conventional digital circuits capacities. Immersive augmented reality interfaces enable intuitive visualizations, helping operators understand intricate search landscapes, facilitating quicker decision-making processes. Edge computing decentralizes processing loads, distributing responsibilities intelligently across heterogeneous device networks, achieving latencies previously unimaginable. As environmental sensing technologies progress, future algorithms must adapt seamlessly, handling ever-increasing volumes and varieties of input modalities simultaneously. Conclusion: from ancient labyrinths to autonomous machines, search algorithms remain central to our quest for intelligent navigation. Their evolution reflects humanity's growing capacity to model complex realities mathematically. To excel in this field, practitioners must master both classical techniques and emerging innovations. Continued experimentation with novel heuristics and cross-disciplinary integrations will drive next-generation breakthroughs, shaping tomorrow's technology landscape.